That's a bit tricky. Think about that. Probability of finding the electron in infinitesimal volume around x equals 1, y equals 2, z equals 0. That's a short answer, but a tricky one. This is the pz orbital. Z equals 0, which means I am talking of the xy plane, which is the nodal plane. Okay, so which of these states will the transition occur? I won't give you that because I have not told you about the transition dipole matrix. Right? The transition occurs, the selection rules I have not told you so well, so I will leave that for it. Most probable point in space. So you can think about these, and I don't know if this is marked for submission. No, so good. Anyway, we were back here somewhere. So the idea is essentially to be able to identify what this particular orbital is, right? And be thorough with that. That's all. So the three basic things that are about, maybe I should show you all these orbitals once more. Just a moment. Are we there? Yes, please. Do you need to? I'll ask you one thing. In the exam, did you feel that way? That you had to remember any of those long equations? Yes or no? So expect the same way. Okay. Now, you get your attendance because after this you are going to collect your answer sheets. So I don't need to record it today. Now, if you look at 3s, right? 3s should have two nodes, two radial nodes, and that is what you get over here. And also you realize that 3s would have if it's got to have two nodes, it must have a quadratic equation. Whereas this fellow had a linear equation. As you go to larger powers of rho, it becomes more and more difficult for the exponential to bring it down, which means that this turning point would keep on shifting higher and higher to larger values of the radius. But in all the cases, so in this case also, this turning point is much close to the nucleus, which is 2p, but if I have 3p over here, right, this turning point goes far off. If I have 3d over here, again, the turning point keeps on increasing, right? So these are the gross features that one needs to look out for these things. But the main feature is that the polynomial is the one that is giving you the number of nodes, right? The exponential is the one that is bringing everything down to 0 at large radii, and rho to the power L is the one that takes care that everything goes to 0, except for these s orbitals. But if I have to, if I have to worry about the probability, so right now what we saw, the start of the class, was that I'll have to integrate over r square sine theta d theta d phi dr, right? So the probability, right? The probability, if I define that by P of R, for a spherically thin shell, if I do an integration of this spherically thin shell, so let's say the surface of a sphere, then I don't integrate over dr, I integrate over all these, right? This is what we saw. We just added dr and we could then integrate over r from 0 to infinity, and we would get the entire, or from whatever to whatever. If I do it for some radius a, I should get 4 by 3 pi r cubed.
So the probability PR of dr, which means that the probability of finding the electron in at a particular radius, which will be spherically symmetric, yes, should be equal to integral over theta and integral over phi, because I want to integrate over this entire sphere. So 0 to 2 pi, if I look at that, I'll write in the same order, 0 to pi, r square. These are all real functions, so or else I could in general write like this, but the